Okay, so I want to talk about what we're going to be covering today. So essentially what I want to take us through is a type of the use of our kind of diffusion control techniques for a type of portfolio optimization. So far you've seen Markowitz type portfolio optimization where you try to maximize return subject to volatility constraints. And that's something that's sort of quite static based on the current state of the market and your estimations about how it's performing. Then you optimize this way. Whereas what I want to do is something where we're actually looking to kind of sequentially invest in time given the wealth that we have. Okay, so we want to kind of forward plan using kind of diffusion control techniques. So this is what leads us to sort of Merton's idea of portfolio optimization. So you might recall that Merton was one of the guys who won the Nobel Prize in economics for developing the Black-Scholes formula. Okay, so one of the things I'll quickly recap before we get going with this is our diffusion HJB equation, because we'll need to use that a fair bit. And we're going to actually focus on solving HJB equations for diffusion control problems. Okay, so that's from this page here. So this is our formula. So the one thing to remember is that if I have some sort of optimization, okay, like this, okay, and I want to look at the if I want to look at the HJB equation for the loss function here, for the value of the system, then I can write it down in, well, one of several ways, but one way to write it is to think of it as the minimum of the instantaneous cost. Okay, so in this case it's C T X of A, okay, and then we minus off the discount factor times the value function, if there is a discount factor, okay, and then we essentially look at our function, if it's L of x, or if it's L of t of x, or whatever it is. What you want to do is essentially find out what the drift term you'd get from Ito's formula would be. Okay, so if I looked at this Lt of x of t as a function of some diffusion process, okay, that depends on time, and I wrote down the drift that I get from that when I apply Ito's formula, okay, then that is the term that I add in here. Okay, so I add on the drift from Ito's formula. Okay. All right. So essentially that's the main idea we're going to be using when we look at our kind of Merton portfolio optimization problem. Okay, so let's actually just define that problem now, and then we'll be using this idea from the HJB equations. Okay. Okay. So we're going to consider a specific diffusion control problem, and we're going to focus on the simpler setting where we have one risky asset. Okay, so that's going to evolve as a kind of stock price would, as some sort of geometric Brownian motion. Okay, and one riskless asset. Okay, so here we've got something like a bank account which gives us a fixed rate of interest. Okay, though as I say, what we do here will actually pass over to the case where there's multiple assets to invest in. Okay, but for now we're going to just focus on one risky and one riskless asset because it's easier to do the theory there, or at least we've not got so many vectors and matrices to worry about. Okay, right, And then for the Merton problem, okay, so this kind of Merton investment problem, okay, you wish to optimize your long-run consumption, okay, so you've got some wealth, okay, and you want to save that wealth over a period of time, okay, or overall time subject to interest, okay, and you want to consume the most that you can out of that wealth, okay, so you're hoping to essentially take back as much money from the investments that you're making. So it's not about maximizing the total wealth, but the taking out the most you can out of your investments while still keeping it healthy, okay? So you may invest your wealth in either a bank account, receiving a riskless interest rate of R, or in a risky asset with value S of t at time t, and obeying the following stochastic differential equation. So ds of t is equal to s of t times the diffusion plus some drift mu t. Okay, so that's going to give us essentially a geometric Brownian motion. All right. Okay, and here b of t obviously is an independent standard Brownian motion. Okay. Now, what we have is we've got our wealth, and we're going to divide our wealth in some proportion between our bank account and between the stocks. I'll say stocks, okay, or risky assets, okay. With S here, we're going to use really to mean stock, okay. So if we do that, let's say N of t here is the number of stocks that we've bought at value S of t, okay. We look at the change in our wealth, then this is going to be the change due to our investments of buying N of t stocks in this risky asset. Okay, so that's our wealth invested in the risky asset. Okay, and everything else that's left, our wealth minus the money that we have invested in the risky asset, is going to go into our riskless bank account. Okay, and receive an interest R. Okay, so that's our money in the bank, the change that it makes due to interest. Okay, and then finally, and most importantly for investors, the amount of money that you can take out and consume and live off and use elsewhere. Okay, so the consumption that you deduct is a sort of rate that you take away, okay, from your investments. Okay, and so here there's essentially two parameters you can control. You can control your rate of consumption, okay, and you can control the number of stocks that you have, okay. So you want to kind of divide between the two of these. You don't want to have all of your stocks in a risky asset. Maybe it will go down and you won't be able to guarantee your income from it, okay. And you've got your consumption, okay. Obviously you don't want to consume everything all at once because you won't have any money to gain in money in the future, okay. But if you consume nothing, obviously you're not going to get much benefit from having your wealth, okay. So we're also going to use in the notes, we're going to let theta equal n of b equal to the sort of the wealth that you have. Okay, so N of t times S of t, which is your wealth that you have invested in the risky asset at time t. Okay, so here I've basically defined a planned equation. Okay, so assuming that S is a geometric Brownian motion like this, then this Wt gives it a planned equation for the evolution of my system. Okay? Alright. So next, we need to have some sort of idea of what objective we're going to look at. Okay? So, given the above planned equation 6, our job is going to be to maximize the long-term utility of your consumption. Okay? So here I've got some function u, okay, and you probably haven't covered too much about utility functions, so let's just discuss that for a second. So a utility function is a sort of a value that you get for saying have some amount of money or wealth or capital or consumption in this case. Okay, and we imagine it like this, that if I plotted the utility that I get from a capital C subject to that capital, okay, then it should look a bit like this, perhaps. Oops. That's not the best drawing that I have ever done in my life, so let me try one more time. Okay, there we go. That's a good picture. Okay, so the idea is that as I increase my capital, then utility, meaning the sort of benefit that I get from having that money, okay, increases. Okay, so that's natural. Okay. If I started out with no money, then the benefit that I get is enormous. Okay, so if I went from having no money at all to having some money, that's going to make a big difference to my life and increase my utility enormously. Okay, whereas if you're over here, if you have a lot of money, okay, then the marginal benefit of having a little bit more, or the same amount more, say £100 more, isn't going to make as much difference as if I had no money and then got £100 more. Okay, so it's quite a typical model of the benefits that people get from their wealth. Okay. All right. Notice also this utility function can be used to give our kind of ideas of risk. Okay. So the idea of a utility function, for example, let's say I had £1, okay, and I could make a bet that would double my wealth with probability of half to £2, or would half my wealth to 0 with probability of half. Well, let's look at whether I would invest my £1 in that bet or not. Okay, so if I just have £1, my utility is here, right? Whereas if I take the bet, half the time I get the utility from 2, and half the time I get a utility of 0. Okay, so on average, if I drew I'll try to draw that line again. On average, okay, if I drew a line between those 2 points, then the average I would get would be this point here, all right? So halfway between the utility from 2 and the utility from having 0. Okay, and you can notice that that lies beneath the utility I get from 1. Okay, so that sort of suggests I'm a little bit, as you say, risk averse. Okay, so this means that I prefer to keep my money and take a bet that has the same average performance. Okay, so utility functions are also used for this idea that you prefer some amount of certainty in the way that you go about doing your investments as well. So that's another reason for wanting to consider a utility function in our objective here. Okay, right. Okay, so enough about utility functions. Let's get back to our objective function. Okay, our objective is to maximize the our long-term consumption. Okay, so here our value function is going to look at the maximum that I can get of investing my wealth in stocks and in consumption. Okay, that should be a belong sign in here. So looking to maximize expected value of that when I integrate over all time, okay, subject to discount factor e to the minus rho t of the utility of my consumption. Okay, so basically looking to maximize my total consumption, okay, given some discount factor. Okay, so you can maximize total expected consumption given some discount. Okay, right. Okay, so again, rho here is a positive constant representing how we discount money over time, how I prefer to invest money today rather than tomorrow. Okay, and I sort of do that in a constant, exponentially decaying way. Okay, UC is a concave increase in utility function, so something like what I've drawn here. Okay, we're going to let P of W0 be the set of admissible policies, so sets of things I'm allowed to do with my wealth. Okay, given the initial wealth W0. Okay, so essentially what I mean here is the sets of N of T's which don't give me, say, negative money in my bank account. Okay, so I'm not allowed to invest all of my money, to double my money in the risky asset, for example. I can only work with the money that I've got. Okay, you can't consume more money than you've actually got as well. Okay. So we're going to sometimes let V of WT be the optimal objective with the integral starting here from little t and WT rather than starting from 0. Okay, so just like we've done previously in the diffusion control problems. Okay, right. Okay, so that's the problem defined. So we've got some stock price going according to some geometric Brownian motion. We've invested some of it, our wealth, in that stock, and some of the wealth in the bank account, and we can control how much money we put in the bank and how much money we put in the stock. Okay, and further, how much money we can consume. Okay, and our objective is to essentially maximize long-term consumption. Okay, or expected long-term consumption. Okay. All right, so now we're going to go about trying to solve this. Okay. So the first question that I have written down for you guys is to think about how we can rewrite this stochastic integral for wealth. Okay, so let's have a look at that. So it says to show that WT is equal to RWT plus mu minus R theta T, so remember theta T is our wealth in the stock, minus C of T dt plus theta T sigma dB of T. Okay, so we've essentially taken our stochastic integral for wealth and just rewritten it now in terms of dt and dB of T. Okay, so let's answer that. So this is just essentially just looking at the definitions. Okay, so note that we had dW of T is equal to the wealth that we have in the bank. Okay, so that's the wealth, total wealth we have minus the money that we have in the stock. Okay, and then we've got the change in our wealth in the stocks minus our consumption. Okay, all right, and I can notice that this guy is theta of T, and then I can notice that this guy is a geometric Brownian motion, so I've got the stochastic differential equation for that guy. Which was this. Okay, and you can notice what I'm going to pick up from this expression is I've got R of WT. So let's look at all the dt stuff. We've got R of WT. Okay. And then I've got minus R here of theta times dt. Then from here, I'm going to get another theta from these two, okay, with a plus mu, okay, which is this guy, okay, and then minus off my consumption. And then finally, the only thing that's got any sort of diffusion bits going on is this N of T, S of T, which is theta T again, times mu, times sigma dB of T. Oh, I should have a D on there, sorry. Theta T sigma dB of T. Okay? So it's going to be helpful coming forward just because we've got our usual kind of Brownian motion and drift term in there, so we've got an idea what the volatility is and what the drift is. Okay? Right, so the next part we're going to look into kind of the structure of the solution. So if we look at the optimal value function, okay, for our wealth at time t, then it's equal to the optimal value function at time 0 times by e to the minus rho t. Okay? So essentially we can notice that we can always work with v of x rather than v of w of t. Right? So that's one of the properties we can notice when we apply a discount factor to a diffusion control problem. And we're going to look for some other properties of this value function, v of x as well, which are going to help us find the solution. Okay, we're going to do that for specific types of utility functions. Okay, all right. Right, so let's look at the answer for this part. So if I look at v of w of t, what is it equal to? Well, it's a maximum over n of t and c of t, okay, of the expected value of this integral. So I'm going to get an integral from t to infinity, okay, e to the minus rho, and let's say s, because we've got a slightly different time here, u of c of s ds. Okay, if I'm being really rigorous, this should be an s as well. Okay. What you can notice is I can apply a slight shift in time, and notice the values of s here should be for bigger than t. Okay. So if I applied a substitution in here, okay, where I shift time so that we start at time 0 and go to infinity rather than from t to infinity, okay. So doing a substitution in my integral, I should go from 0 to infinity, and then the appropriate time shift replaces s by, let's say, tau plus t, okay, and I get u of c of tau d tau. Okay, so let's substitute for s, I put in tau, where tau and s are related by s equals tau plus t. Okay. I should go, that'll be over n of tau and c of tau for tau greater than 0 now. Okay. And you can notice all this is done is taken, so essentially just shifting time a little bit. We notice the only thing we're going to pick up out of here is an e to the minus rho of t term, and I've got exactly the same optimization I did before for the value function started from time 0. Okay. Okay, so essentially the only thing that's affected by doing this is essentially we've multiplied each term here by e to the minus rho of t. Okay, so that's quite a common feature that we found in discount factors previously, even in the discrete time setting. Okay, right. So that's one thing to note. The next thing we're going to look at is into this HJB equation for this problem. Okay, I've written it down two different ways. So what we can say is that the HJB equation is equal to this. So this would be our, remember it's of exactly the same form as before, so we've got 0 is the maximum over the sets of actions that I can take. Okay, then I've got the utility that I get, the instantaneous reward that I get, minus the discount factor times the value function. Okay, so I'm working with the value function v of x here, where it doesn't depend on time. Okay, and then we should get the drift term from Ito's formula. So we want this part, we want this term to be the drift from Ito's formula. Okay, and then I've said that I can write this out in a slightly simplified form up here, where I separate out the maximizations of consumption and the maximization involved in our investment. Okay, and you can see that's true from this expression. If I just pick up the terms that are to do with C, then I've got this term is to do with C, and this term is to do with C. Okay, and that's it. So that just gives me this expression over here. Then I pick up the terms that are to do with theta, which is essentially this term here and this term here. Okay, you see I've got this bit here, and then all the remaining terms, these which don't have anything to do with theta. Okay, right. So given what really remains to be checked is that essentially this is the drift term that I get if I apply Ito's formula to V of x. Okay, because we know that the form of the HJB equation is the instantaneous cost minus the rate of discount times the value function plus the drift term I get from Ito's formula. Okay, we can see that this follows from that. Okay, so what remains to check is just that this is to check what I get from Ito's formula when I apply to this guy. Okay, so let's do that. So if I apply Ito's formula to V of W of t, okay, well W is our wealth, and I get, okay, so the normal application of Ito's formula says that I get a partial derivative with respect to V of W, and I times that by dW of t, and I get a half dW applied twice, okay, V of W d, oh, I should be careful, the quadratic variation, okay, of W. Okay. Right, so I need to work out what each of these individual terms are. Okay. So for the first of these I can use my answer from above. Okay. So I've already written out what dW is. So let's just write that out again. It's just above. Okay, so remember that dW of t we showed above is equal to R of W plus mu minus R of theta of t minus C of t. Okay, and all of that was given dt plus theta t sigma dB of t. Okay, and this also helps us remember what the quadratic variation is going to be. Remember, the quadratic variation is the part that we pick up from our Brownian motion term. In fact, when we get a dt times the square of these terms. So we essentially take the dBt term, we turn it into a dt, and then we square this term, and that's what we substitute in for this guy. So this, given this part, is going to be theta t squared, sigma squared, and we replace the dBt with the dt. Okay. Alright, so we're going to get plus a half second partial derivative of w times theta t squared sigma squared dt. Okay, so if I simplify all of this, okay, and I look at the drift term that I get from Ito's formula, I'm going to get RWT mu minus R theta minus C of t, okay, times the partial derivative with respect to W of, V of W of t, okay, plus a half second partial derivative of V of Wt, theta squared, sigma squared, and all of that is dt, and then I've got my final diffusion part, which is the partial derivative of V times theta t sigma dB of t. Okay, so then I just simply note that, remember that I was looking for the instantaneous cost minus the discount factor times my value function, or discount rate times my value function, then added to that the drift term from Ito's formula. And here's I've written down Ito's formula, and this is the drift term. Okay, notice this drift term is exactly the same as this up here. Okay, right, and so we see that these are two valid forms of the HJB equation for this Merton problem. Okay, so we're done. Right, okay. So next thing we're going to have to go about trying to solve this a bit. Okay. So one part of this optimization is not too difficult to solve. Okay. So we've got this maximization of theta, a linear term plus a quadratic term. Okay. Okay, so show that optimizing the HJB equation over theta, that we arrive at theta star is equal to this. So the ratio between the two partial derivatives times sigma to the minus 2 times mu minus r. Okay, so that gives us a proportion of wealth that I should have in my stocks. Okay, let's do the answer to that. Okay, so remember that we had from the HJB equation that the part that involves theta was maximization, okay, of theta mu minus r plus a half sigma squared theta squared, and then the second partial derivative of v. Okay, so let's just maximize that, and note that typically we'll expect this value to be negative. It's related to a concave function. Okay, so we're going to expect its second partial derivative to be negative to kind of preserve that concave property. Okay, so this is nicely well-defined maximization. Okay, so implies, so if we differentiate this with respect to theta, I'm going to get mu minus r plus theta, sigma squared theta dw of v. Oh, notice I'm being a bit sloppy. This should be multiplied by, apologies, let me just make a bit of space. This should be multiplied by dv here. That's my bad. Okay, so we need this to be equal to 0 for a stationary point. So if we differentiate this, we're going to get this and for it to be a maximization, we set it equal to 0. Okay, and then they just rearrange, and they get the theta star is equal to, so move this onto the other side, I'm going to get a minus partial v mu minus r times sigma squared, sigma squared to the minus 1, okay, and then I'm going to divide out by this as well. Okay, alright, and that's as required. Okay. Okay, and then it says that given theta star above, show that the HJB equation now becomes this. Okay, so essentially we just need to substitute in our answer into this expression here. Okay, and I'll leave you maybe to check at home that that's going to give you this expression here. Okay, so if I put in theta star into here, then I'm going to get this. Okay, I'll just leave you to check that. It's not a difficult calculation. Okay, right. Okay, so anyway, so we've got an idea of what the wealth that I need to maintain in my stock is. Okay, and that's the wealth I need to maintain in my bank account. Of course, I haven't found out what V is yet, capital V. So you need to kind of characterize V, or have some more information about it in order to evaluate what these partial derivatives are. Okay, so what we're going to do now is we're going to focus in on a specific type of utility function, one that's got a nice structure, so we can find out what these partial derivatives are in order to find out what the optimal wealth is, and then also to figure out what the optimal consumption is. Remember the optimal consumption, we also need to know what these partial derivatives are in order to do this maximization here. Okay. So specifically we're going to work with a utility function that has constant relative risk aversion. Okay. So I'll probably set you a question to think about what constant relative risk aversion means. Okay. But roughly speaking, it means that I don't care, well, consider the example of a bet that I wrote down before. Okay. Where I had £1 and my attitude to a bet of £1 compared to a bet, say, of doubling my wealth and losing my wealth, okay, I had a certain attitude towards that bet at £1, okay? But let's say we considered the same bet, but now it's £100 and I could win £200, okay, or end up with nothing, okay? Then I could consider the situation where my attitude to that bet is the same, okay? Where the decision I make is exactly the same, okay? Now, the sorts of utility functions that have the property where you make the same decisions over bets, regardless of your relative wealth, okay? So it doesn't matter if it's £1 or £100 or £1,000,000, as long as the relative size of the bet stays the same, then your attitude remains the same. Those are called Cara utility functions, okay? So have constant relative risk aversion. So we're going to work with utility functions that have this constant relative risk aversion property, and it turns out that those utility functions have a specific parametric form, that they look like this, okay? That your utility of your consumption is the consumption to some power, okay? In particular, we write it in the following way, where the consumption is 1 minus R divided by 1 minus R, and R is sometimes called the sort of constant of relative risk aversion, okay? Or coefficient of relative risk aversion, okay? Okay, so we can do a little bit of theory about that to explain why that is the right form for this type of problem, but for now let's just say we're working with a utility function which looks like this, okay? So we want to solve the Merton problem, this Merton portfolio optimization problem, in order to maximize this function, okay? So we're taking the integral of the discounted consumption, utility of consumption, where the utility is given by this now. Okay? And essentially, what we can show is because this is a power function, we might get some sort of power function form out of our value function here, v. Okay, and that's going to help us a lot in evaluating what these different derivatives are doing. Okay, so let's have a look at that. Okay. So essentially what we've done here is we've considered the value function times by lambda, where lambda is some constant. Okay, so essentially multiplied by our wealth by lambda. And we're going to claim that that corresponds to having the same wealth w and multiplying everything by 1 minus r of lambda. Okay, so let's just have a look at what our objective function looks like there. So here I've got a maximization again over the number of stocks I have, the amount of consumption I do, and that maximization is over the sets of policies which work when my initial wealth is W0 times lambda, okay, or W times lambda I should say, okay, and the maximization that I'm doing is exactly as the same as up here, okay. Okay. Now let's think about this. Instead of having a policy where I've got lambda times W, I could consider exactly the same situation, okay. Each policy that I consider here is the same as a policy where I have n of t and I consume lambda c of t, okay, but I have an initial wealth of w, okay, because everything I could do here, all right, with this wealth, I can also consider as an investment where I just multiply everything by lambda, okay? So instead, I've just essentially just sort of renormalized the money, okay? So the units aren't in terms of units of lambda, but I mean units of 1, and instead I have them in units of lambda, okay? So it's essentially just a changing of the units in some sense. Okay, so here, instead, I'll be doing a maximization over, in this form, n of t, c of t, belonging to the initial wealth. W, okay? And what I can do, in order to rephrase it as it was here, I just multiply everything by lambda, okay? Specifically, in this expression, I've got the same discount factor, but my consumption is essentially multiplied by lambda. Okay. Okay. So essentially we can say that if I multiply double my wealth, I just could do the same investment policy, okay, take a one where I didn't have double the wealth and just double all the numbers. Okay, that's fine. So if we look at what effect that has on this specific utility function, all I've done is multiplied that utility function, okay, the one from wealth W, by lambda 1 minus r. Okay, so notice I've just got lambda 1 minus r is the only thing that depends on lambda in here now, and everything else is exactly the value function from before. Okay. So because of the form of our utility function, if I multiply by wealth, by lambda, it has the effect of just changing the value by 1 minus r to the lambda to the power of 1 minus r. Okay. So then the next part says to argue that v of w has this specific form. V of w equals gamma, the well, w, to the power of 1 minus r divided by 1 minus r. Okay? But that's sort of obvious now. I could take lambda, for example, if this expression always holds, okay, I can take lambda equal to w to the minus 1, okay, in here, and then I'll get v of w here, I'll get w to the minus 1, 1 minus r, and I'll get v of 1 here, okay, and I can take gamma just to be equal to 1 minus r of v of 1 in this expression. Okay, so when I've got v of 1, okay, then I could substitute in gamma here and I'd end up with this part. Okay, so it's not too hard that. We just substitute in some values and just say this is a slightly nicer form. Okay, or slightly cleaner looking form. Okay, right. Alright, so now next bit. So now that I've actually found the form, a parametric form of the value function, okay, we notice that instead of it being potentially anything, we've noticed it's a power function in the wealth and there's some constant that's multiplied onto it, which we don't know what it is quite yet. Okay. And it's now, the way we're going to proceed is a bit like the way we looked at the LQR's theory. We want to kind of go about looking at, we know the form of, guess the form of the solution. It's v of w is this kind of power function. Okay, so given that guess of the form of the solution, we want to look into the HJB equation and see which parameters work in terms of this gamma to give us a solution to the HJB equation. Okay, and then once we've found that solution, then, well, we hope we've got an optimal solution. Okay. So one of the things that we need to know about is these partial derivatives, okay? So I can leave you to calculate these at home, but notice that the partial derivative in w of v is equal to gamma w to the minus r. That should be clear from this form. And if I differentiate this one more time, and ignoring this x, which is a typo, then we should end up with this, that we multiply minus r on the front, and then we deduct the power by 1. Okay, so just normal differentiation. Okay. All right. So that sort of gives us some good progress because we can now, you'll notice that we've got the form of our theta here. Okay, I haven't written it down yet, but notice I've got the terms here. Actually, the gammas will cancel out, so I actually know what the form of this solution is. I know how much money I should invest, okay, of my stocks, but I don't know how much I should consume necessarily, okay? So now we're going to look into the consumption part, okay? So here we say, shows that when optimizing over C, the HJB equation is optimized by C star, okay, which is equal to gamma to the power of 1 minus r times w, okay? So the answer to that okay, so recall that from the HJB equation we had one term that was a maximization in C, it looked like this, u of C minus C times the partial derivative of v of w. Okay, so if I maximize this, I can differentiate both sides and get that I get this condition. Okay, and then I know the form of the solution of this is just gamma of WR. Okay, then I also know from the form that I've assumed of the utility function being a carrier utility, that this is c to the minus r as well. Okay? So overall, this is going to imply that c is equal to gamma to the 1 over r times w. Okay? Then we can substitute this back into the expression that we had in terms of c in the HJB equation, and we can show that it's equal to r divided by 1 minus r gamma to the power of 1 minus 1 over r times w to the 1 minus r. Okay, so let's just do that quickly. That's just a substitution step again. So answer, max for c of u of c minus c times partial derivative of b is equal to, well, u of c star, where c star is what I've been given here, minus c star partial derivative of v again. Okay, and now I can substitute in all the values that I've got. Okay, so I'll just quickly remember that u is equal to c star to the 1 minus r times 1 minus r minus c star times the partial derivative of v. Okay. Okay, so I'm going to get out of all of these expressions. So from this part, I'm going to get gamma to the 1 minus r w to the 1 minus r divided by 1 minus r, and I'm going to minus off c, which is equal to gamma to the minus 1 minus r. Oh, sorry, I just got minus sign on there. 1 minus r w, and then times the value function, the partial derivative of the value function, which remember is gamma to the w to the minus r, and then I can collect all these terms together. I've essentially got 1 over 1 minus r, and then I've deducted off 1 lot of this expression. Okay, so all I'll end up with is r divided by 1 minus r, gamma to the power of 1 minus r times w to the 1 minus r. Okay, so you notice in both sides here I've got a gamma 1 minus 1 over r, and I've got a w to the power of 1 minus r on both of these sides, so it's just collecting the coefficients together. Okay, good. And then the final part here, okay, which I'm going to ask you to do as an exercise, okay, is to show that gamma star is equal to this expression. Okay, so where kappa in this expression is equal to sigma to the minus 1 mu minus r. Okay, so what do I really want you to do here? Okay, I'll give you a big hint as to how to solve this question. Is I essentially want you to substitute this into the HJB equation where it's supposed to go. So in the HJB equation it's supposed to go here. I've told you what this part in the HJB equation is. That's here. Okay, that's it here. Okay, so essentially what you're going to be left with is a bunch of terms that have no maximizations in them. It's just lots of partial derivatives in v. Okay, and I've told you what the form of v is as well. It's this form. Okay, so the only thing you don't know now is gamma. You figured out what c is, you figured out what theta is, and the only thing that's left that you don't know is gamma. Okay, so then you can substitute those into the HJB equation. Okay, and then it's a matter of you solving for what gamma is. Okay, so I think that's a good exercise for you to kind of figure out. a little bit how to do some of the substitutions with the HJB equation. Okay, so I'm going to leave that as an exercise for you for doing as your homework assignment. All right. Okay, so now what we can notice is we've actually kind of solved everything we need to know. We found that if I have my initial wealth W, then this term, okay, which notice that is the partial derivative divided by the second partial derivative, okay, gives me the amount of money I should invest in the risk E, the amount of my wealth I should invest in stocks, okay. Then this is the amount of wealth that I should consume, okay, when the constant in here is given by this expression here, okay. So we've basically found a set of parameters, given you've got a carry utility, we found a set of parameters that optimize your investment, okay. Okay, so we've proven that this is a solution to the HJB equation, but we haven't quite done all the mathematical bookkeeping, as in we'd need to really prove that this actually is an optimal solution. In sort of a more applied setting, I'd say, well, you solved the HJB equation, so you've probably got an optimal solution, okay? But if we're going to be really mathematically rigorous, then we need to kind of prove this, okay? All right, so what we'll do next is some of the sort of more mathematical details of proving that these parameters, okay, and proving that when I found a solution to the HJB equation for this problem, then I have indeed found a solution, an optimal solution. And what we're going to rely on is this Davis-Farrier-Martingale principle. Okay, right, so I'll cover that next. Okay, great, thanks.